you very much. So, let's continue our discussion of the problem of obtaining sharp, perhaps up to the endpoint, one estimate for spectral localized estimate for the wave propagator associated with the sub-Laplacian. So, as we mentioned, the problem that now we are asking about is whether we can have this bounds for the spectral localized version of the wave propagator, so the cosine family generated square root of the sub-Laplacian, and we ask, I mean, when we spectrally localize with this localization parameter, so the spectral parameter lambda, then whether we can have this kind of growth, polynomial growth as a power of lambda, and in particular, we are interested in understanding what the best possible alpha, what is the best possible exponent here is. And so we call the infimum of these alphas actually alpha naught associated with the operator that we are interested in. And we know that in the case of the standard Laplacian on RD, this kind of estimate holds true with alpha naught being the dimension -1/2 of the environment space. And we have seen that actually by the subordination argument, this d-1/2 threshold for the wave equation for the wave propagator gives the d/2, so this +1/2 that comes from this Cauchy-Schwarz inequality, the sharp estimate for a one-nonce of more general functions of the Laplacian, so corresponds to the d/2 threshold in the matter theorem, for example. So we expect that if we have a similar behavior also in other settings like that of sub-Laplacians, then if we want a similar estimate with d/2 also for multipliers, we would like to have a similar threshold d-1/2 for the wave equation. And indeed, we know this is the result at the rest time 1999 that actually for the sub-Laplacian, the isotropic sub-Laplacian emission of the Heisenberg group, and more generally by Müller-Zayer's result for Heisenberg type groups, actually we do have this kind of estimate. So I'd like to try now and discuss some ideas that come from a different proof that we developed in collaboration with Detlef Müller, which allows us to generalize this result in the case of Métivier group, so to avoid all this kind of isotropic kind of assumption. So we allow for different coefficients on the sum squares or more complicated underlying structures in the Métivier group setting at least. And somehow a different approach that is much more relying on the underlying geometry. And so in order to introduce some of the basic ideas, we discussed, I mean, the fact that one of the important properties of the wave equation is finite propagation speed. This can be also proved, it's a classical result for the wave equation driven by an elliptic operator, but actually mirrors show that this also is true in greater generality for also some elliptic operators, so such as sub-Laplacians. And indeed, when you write this, so the fact that the support of the, in this case, the convolution kernel, if you're working in a group setting, but measures result is in general for manifolds, you have to write it in a slightly different way. So that the support of the wave propagator at time, the kernel, the convolution kernel of the wave propagator at time t is contained in a ball associated with the underlying sub-Riemannian geometry centered at 0 and radius the time part of the propagation. Okay, and so by using this consideration with some geometric heuristic combined with the geometric heuristics, I mean, we saw that by a sort of Cauchy-Schwarz argument, a very elementary one to ignoring Schwarz states, we are actually able to guess that definitely this quantity, so this one norm of the convolution kernel that corresponds to the operator and one norm in the case of this group invariant operators, actually it's definitely at most lambda to the q/2. Okay, and so this is definitely something much larger than what we would expect if we really are aiming at this. But at least in the Euclidean case, somehow this almost matches the right result up to this missing somehow quantity 1/2. And what we mentioned is the fact that actually one could recover even this 1/2 if one were more precise in this sort of Cauchy-Schwarz inequality, in the sense that one should actually imagine that the main part of the mass of this propagated solution is not really on the whole ball, but just around the singular support of the wave propagation. And so now the question is, what are kind of techniques we can develop in order to understand better this? Because this is actually the method that has also been used to prove analogous results, not just for the Laplacian on RD, sourced by Ignacio and Peral, but has been generalized and obtained somehow in order to give a result that actually works for more general elliptic operator on manifolds, and this is this result by Seger-Sockenstein. So estimates for an integral operator that then leads us to also sharp multiplier estimates in this generality of compact manifold, but for elliptic operators. And so I'd like to tell you a few words about the ideas of this argument, and then, I mean, because in a sense, the spirit of our newly developed approach with Detlef-Müller is really trying to follow that approach in order to get the estimates also in the case of the sub-Laplacian. And so in the case of the elliptic, so the standard Laplacian on RD, of course, we have a very explicit, in a sense, representation of the wave propagator just by using the Fourier transform. So if we take, say, a time one, because as we know, I mean, here by homogeneity, by scaling, considering time one is enough, we take this spectral localization, and we just take the convolution kernel, because again, we have optimization in values, of course, in RD, and we can write this up to some constant as a sum of oscillatory integral operators of this mode. So there's a plus and a minus in order to get, I mean, the cosine as usual sum of imaginary exponentials. Okay, so this square root of L in the Fourier transform, of course, in the case of the Laplacian becomes not itself. And so we have effectively an oscillatory integral Fourier integral operator where the phase function up to the choice of plus or minus is something like this, so x dot xi plus mod xi, say, and this phase function encodes a number of important properties of this object. In particular, so this is of course one homogeneous psi, and if we look at the gradient of the differential inside of this phase function, this, and in particular the vanishing of the gradient, the critical points inside the phase function give us information indeed on the singular support of the wave propagator. So we just compute the gradient and we see we get something like that. And this vanishes if and only if x is minus psi over xi, which of course belongs to the unit sphere. And so here, from this kind of computation, one starts recognizing this kind of geometric information that we expect a singular support of the unit sphere of radius 1, and indeed choosing the various directions of this frequency parameter, we get different geodesics in some sense that lead the origin in different directions and give you all the points of the unit sphere. But then we have more information that we can exploit. So on the one side, we can consider the mixed Hessian of this phase function. This case, of course, we can also differentiate in x, and we just get the identity. So this is on the general mixed Hessian, and this is one of the ingredients that one can use in order to justify the application of this method that is the key method using this paper by Seger-Sockenstein. Paper 1. In order to actually get N1 estimates for this kind of operators. And this method is effectively based on a further decomposition of the frequency space that here you see is localizing this annulus where psi is of size lambda into further angular sectors. So let me just show you a picture for that. So you are localizing this annulus of size lambda, and then you just split it into sufficiently small angular sectors in such a way that the angular aperture will be lambda to the -1/2. And then, as it happens, by using this kind of splitting in each of the sectors, effectively one can linearize the phase. And this linearization then allows one to effectively treat the contribution of each single piece as a sort of a modulation to a particular fixed cutoff, which gives you one unit contribution to the L1 norm. And so at the end of the day, in order to estimate the L1 norm of the whole thing, you just sum these contributions, and you just get that the number of pieces that you need in this case, if you do the maths, is actually number to d minus 1 over 2. And so it's just, this is the way to actually prove the L1 estimate that has been used. And just let me point out that on the one side, in order to justify that each of the species has unit contribution to the L1 norm, one has to do a number of, say, integration by parts inside in order to actually show that each of the species has the right, satisfies the right estimates. And so there is a certain importance in having sort of uniform estimates on the phase and its derivatives, which at least in the case of RD is quite simply seen because of somehow the very simple expression for the phase, but in greater generality, one might need to add some additional compactness assumption on the whole sort of dependence of the variables of the vector parameters of the phase in order to ensure that you do not have unexpected blow-ups and you have indeed a uniform estimate. Okay, so just leave it like that, but let me also point out that actually, I mean, this linearization of the phase will give you some sort of modulation effect there. If you look at it on the space side, actually contributes to the fact that this kind of dual boxes that you can see on the space side will just gets translated, and each of these boxes gets translated in a different direction corresponding to the sort of direction of the tube on the frequency space, so that effectively if you then look at what happens from this point of view of the frequency decomposition on the space side, you can actually justify that indeed most of the mass of the spectral class part of the wave propagator lies in this angle. So a posteriori, one knows that indeed this is this kind of essential support. And so again, a posteriori, this more refined Cauchy-Schwarz argument would also be justified. Okay, so it's just to mention that this Segers-Ogenstein method of splitting this annulus into angular sector very much matches with this geometric heuristic dimension. Okay, a second observation I'd like to make here is the fact that we can also look not only at the mixed Hessian, but also at the psi Hessian of the phase. And here, if you just do the computation, things are slightly more complicated. Here, this just goes away to remain with this piece. And so you should get something of this kind, which is no longer full rank, but this is to be expected because by homogeneity consideration, you cannot get sort of curvature in the radial directions, but this is rank b minus 1. So the maximum rank you can have given the homogeneity. And actually, by working with this kind of information and applying an appropriate, so to say, doing an appropriate application of the method of stationary phase, one can actually use this rank information to deduce that this estimate is actually optimal. Of this b minus 1 over 2 that comes into this estimate. Okay, so from the phase function and its sort of properties, you can actually deduce both the result that you would expect for the wave equation, and also somehow that it can be improved because of the non-degeneracy of the phase function in this case. Okay, so that's what one can do in the Euclidean case. And interestingly enough, this is actually part of the content of this Anna's paper by Segers-Ogenstein. This method actually applies, of course, to more general Fourier integral operator as soon as you have appropriate sort of assumptions on the phase function. And in particular, this can be used to prove optimal, at least for small time, estimate of Miach type with this exponent t minus 1 over 2 on any compact manifold whenever you have an elliptic second order Laplacian differential operator. So if instead of the standard Laplacian on RD you take an elliptic operator, so a Laplace Beltrame operator and a compact Riemannian manifold, something like that, you can effectively reproduce this kind of argument. Let me just try and point out some major feature of this kind of generalization. I mean, just to these ideas. And one of the interesting facts in this kind of argument is that one can see very much the relation with the underlying geometry. That is, whenever you have an elliptic Laplacian on manifold. And here, for a moment, I'm leaving the setup of sub-Laplacians or left invariant operators. I mean, this is not, there is no longer a group acting just for this piece of the discussion. So you can have a principal, you can consider the principal symbol associated with this Laplacian. Which will be a non-degenerate, so actually positive definite quadratic form at every point of the manifold. So, I mean, thought of as a function of the, so to say, frequency variable and the tangent space, you have this kind of equivalence, maybe constant that depend on the point, if it's compact, and of course this will hold somehow uniformly as soon as you choose appropriate coordinates. Well, anyway, you have this kind of situation, and then there is a relatively classical theory, which also before the work by Sevius of this time, that tells you that one has an FIO representation, at least locally for small time, of the wave propagator. Or more in detail, what happens is that locally and for small times, one can write the wave propagator associated with this elliptic Laplacian as effectively FIOs of a certain form. So we have phase function which will depend on time, space frequency variables, and amplitude. Function. So it's not as explicit, of course, as you have it on a B, but still there are a number of pieces of information you can get from this representation, and in particular, where the phase, which is real valued as before, and one homogeneous side, so to say, parametrizes what is called the canonical relation of transformations generated by the square root of the principal symbol on the cotangent path. So what I mean by that is that we can consider the Hamilton flow or geodesic flow on the cotangent bundle associated when you, by thinking of this as square root of the principal symbol as the Hamiltonian function of the cotangent bundle. So you will have some curves which are parameterized by initial point and initial covector and the corresponding evolution of the covector on the bundle, which satisfy appropriate Hamilton equations. So, like the derivative in time of X would be psi This is the Newtonian. Okay, so the flow curves certain vector field on the tangent bundle. With initial condition times where this is 1. Okay, so this is the geodesic flow, thought of as a projection of the manifold as a flow on the cotangent bundle. And then what does it mean that the phase is associated with the canonical transformation used by that? It means that the phase has a gradient inside which vanishes if and only if the point x is actually the endpoint of this geodesic, starting with y with initial covector psi. So this corresponds to the fact that we're seeing in the Euclidean case that these critical points of the wave propagator really correspond to these endpoints of geodesics. And on the other hand, at those points, we have that actually the next of the phase is given by this other psi t, and the mixed Hessian is non-degenerate, those critical points. Okay, so there is a relatively classical theory. There are a number of different possible constructions for this FIO representation, but all of them have in common this kind of feature, that is, that the phase function parameterizes this kind of transformation, which is induced by this cotangent space sort of flow that is induced by this square root of the principles. Okay, so if you work out what this means in AB, you will get essentially what we had before. But let me just point out what we can deduce from this information. Well, one thing is that this kind of non-degeneracy of the mixed Hessian, with some care because one needs some uniformity there, we can apply the method of Seghers-Augustin. It's applicable. I won't enter into details, but effectively, again, one can analyze this operator, but by doing this kind of splitting into first, of course, the frequencies will be split with the parameter lambda, and then again, you can do this angular splitting and so on. And with some work, one can indeed get something like that. This kind of spectral localized portions of this FIOs indeed satisfy this kind of expected estimate that we had before. It's not there, but that's more or less the idea. And so we get this estimate, and this is enough for Bianchi-Perral estimates for an elliptic Laplacian L for small time. And this is effectively because we are working on a compact manifold, so even if this representation held only locally up to certain smoothing terms and so on and so forth, you can just put together a finite number of pieces from, related to the various coordinate patches you may use in order to obtain this kind of representation in general. Okay, so we know that at least for small times, the same estimate we have on B for the wave propagator, we have also on any manifold of dimension D when the wave equation is driven by an elliptic Laplacian. And on the other hand, if one looks at this kind of condition, we know that the gradient of the phase inside computed in x equals xt is always 0. So then if you differentiate this relation inside further, what you get chain rule is effectively this. And so you see you have some sort of relation which involves both the mixed Hessian and the Hessian inside, and this kind of differential inside of the map xt, which is essentially related to the differential of the geodesic exponential map. So as it turns out, so we know that this is non-degenerate. This one has rank, the maximum rank you can have again by homogeneity consideration is d-1, and it has rank d-1 away from so-called constants. So somehow points where the differential of the exponential map degenerates, where you might have loss of geodesics with length minimizing and things like that. Okay, so in away from constants, this will have maximum rank, and then because of this relation, you can deduce that this guy also in the same points is maximum rank, and this would allow you to apply stationary phase to get the optimality of this d-1 that you have spoken. Okay, again, very quick fundamental ideas from this discussion, and we can make these things more precise. But one key point here is the fact that in this elliptic situation, actually, you have on a compact manifold, when you have an underlying Riemannian geometry, you have what is known as an injectivity radius. So that maybe geodesics may stop being length minimizing after a certain time, may start having a sort of chaotic behavior one way or another, depending on the manifold, but at least locally, you think, say, of the sphere as a manifold where if you use the standard Riemannian metric, geodesics, say, emanating from the pole, look like the geodesics on RD, close to the starting point, and maybe then start self-intersecting, and you might have sort of caustics in large time, but in small times, this kind of phenomenon doesn't happen. So that is why effectively one can more or less reproduce, at least locally for small time, the same kind of geometric phenomenon you expect on the Euclidean setting, and then get that the estimates you get in the Euclidean case with some work, you can also get, and they are optimal also in this setting of Riemannian manifolds. But the point is that, as we have just seen with this, for example, in the case of the Heisenberg group, is that the sort of say what this wavefront look like is not really spheres just centered at the original point, but they have a much more complicated situation behavior. I mean, this is sort of just a portion of this surface of revolution that we discussed yesterday in the case of the Heisenberg group. This is an attempt of drawing something similar in the case of a non-isotropic Heisenberg group. Of course, I have to reduce dimension because this would have to be dimension 5. But if you try at least to choose particular directions with some partial radiality, you get some picture which are even messier than the one you would have in the Heisenberg, the standard isotropic Heisenberg group case. And so the problem is, how do we understand what is going on there? And what I'd like to point out is that in this case, actually, there is no way you can be sure you get even this kind of information, because caustic points accumulates towards the starting point of the geodesic, in the sense that if you move your psi, this initial codirection, towards somehow the singular, the singularity of the principal symbol when it starts vanishing, well, then the cut time, so the minimum cut time where this you get this kind of degeneracy of the sub-Riemannian exponential map becomes smaller and smaller. So you get this kind of cut points which accumulate toward the starting point of the geodesic, and this makes it so that you have no chance of having an injectivity radius or something like that that would allow you to actually treat this problem in the same way. Okay? Nevertheless, one thing that one can do is, in the case of a sub-Laplacian, This is true actually on any sub-Riemannian manifold. Here, the principal symbol is a positive semi-definite form. And at every point, you might well have vectors psi where the principal symbol vanishes, so it's semi-definite, that generates a certain codirections, and this codirection actually corresponds to the annihilator space of the horizontal distribution at that point. So in the elliptic case, the horizontal is the whole tangent, so the annihilator is 0, and conversely, instead, if you have fewer directions which are horizontal, then you will have this kind of no space of the principal symbol become non-trivial. So you have a subspace of bad codirections in your frequency space where the principal symbol vanishes. Okay? And of course, I mean, you may think of the Heisenberg group, you may choose coordinates as the sort of plane that describes the horizontal direction fields, at the same time also this kind of bad set of codirection will be corresponding, because it's like the orthogonal subspace. Okay, but then what one can do is that by micro-localizing around point x0 and in the manifold and away from the corresponding say loose space for the quadratic form. So effectively you choose a conical neighborhood in the cotangent space which stays well away from this region. Well, for sure you may ensure that this locally when x is close to a certain point and psi is in an appropriate neighborhood, so to say, away from this bad set, that actually you do have ellipticity property, at least in a certain conical region. Of course, it's not much, but at least there is some ellipticity. And actually, because of this, in a previous work with Detlef Müller and Sebastiano Nicolussi-Golo, we could show that because thanks to this kind of microlocalization, we can obtain an FIO representation for part of the wave propagator, okay, which of course is somehow localizing frequency in a particular region which sort of cuts out the bad directions for small times and near certain points. And so we can get something like this. Also, for, again, not for the full wave propagation, but only up to a certain sort of microlocalization. And then we would like at least to try and see whether we can prove some non-degeneracy. So this kind of stationary phase argument that would at least tell us something about some necessary condition for this kind of estimate. And we, as I mentioned, you cannot expect to have for free the non-degeneracy of the differential exponential map, but people in sub-Riemannian geometry did study this problem on arbitrary sub-Riemannian manifold, showing that there are many non-degeneracy points for the sub-Riemannian exponential map on any sub-Riemannian manifold and sub-Laplacian. And because of this reason, even after this microlocalization, we can find some good direction in which we can prove that this guy has the maximal rank, which means we can prove that at least in certain regions we have that our phase function does have the rank it should have, and so we are allowed to apply the stationary phase method And at least this gives us a universal lower bound for the wave equation associated to any sub-Laplacian on any sub-Riemannian manifold, and tells us that indeed we have this kind of lower bound, and with some additional work, we have the same result for any sub-Laplacian on any sub-Riemannian manifold. So if you remember what I told you some lectures ago, the fact that the trivial lower bound for the multiplier estimate would have the horizontal rank, in a previous work we did that we could, by using more explicit formula, show that actually you always have this lower bound on two-step stratified group. This FIO approach I just described actually allows to combine with this geometric information on the non-degeneracy of the sub-Riemannian geodesic flow to get this lower bound universally for any sub-Laplacian on any sub-Riemannian manifold. So we cannot go in any case below this d over 2, and similarly for the wave equation corresponding. This, of course, is not proving that the result is true, but at least that indeed this bracket generating condition is the only thing that is needed to show that you cannot go below half of the topological condition. So this at least has something to do. This geometric parameter has something to do with this kind of. Okay, so this is sort of a different proof, more geometric in character for the lower bound. And as I said, this now holds on any step, no longer two-step, on any manifold, doesn't need to be a group or anything like that. But then, of course, remains the problem how to actually prove the reverse inequality. And so to get this condition, at least in some cases, is sufficient. And the work that we have been doing more recently with Detlef was really to try and develop an alternative approach, still trying to follow this kind of one. Okay? But it turns out, interestingly enough, that at least in the elliptic case, one can prove that there is a topological abstraction for this kind of representation to hold beyond caustics again. So somehow one would need to try and find a way to avoid this kind of decompositions, because if you then start trying to get the whole wave propagator, in principle, you might want to sort of maybe decompose dyadically this region. But then, I mean, if you take a much larger set here, you have to take much smaller time, because then things become more problematic sooner or something like that. So it doesn't seem to be particularly feasible to actually try to approximate the wave propagator with this kind of just micro-localization where you can get this kind of representation. And so, in a sense, if we'd like to get a sort of full representation that doesn't have this problem, in a sense, it seems that we need to find a different kind of representation that allows us to go beyond caustics. And we discovered that actually this is possible by dropping the assumption that the phase function is real bound. So this topological abstraction that is there, at least in the elliptic case, for real value function is no longer there when you, instead of using the real value phase function for the representation, use a complex value phase function. So now, in the remaining time, I'd like to tell you something more precise about this approach that we developed with Detlef Müller that recovers the result of Müller and Stein 1999 for the sub-Laplacian, the wave equation driven by the sub-Laplacian on Heisenberg group, but extends it also to non-isotropic sub-Laplacians, and so also to this kind of second picture, and also to the more general MTBA group case. Okay, so let me just tell you a few words here about that. So we are working in this context, just for simplicity, on the Heisenberg group. The principal symbol now has this kind of shape, where we have this skew-symmetric matrix that is 0, that also appears if you write the product formula appropriately in the product. And so here we are working on Hn, so the dimension, topological dimension is 2n+1, the homogeneous dimension 2n+1. So what we would like to get is this kind of spectral localized estimate for the wave propagator. And when I put a double twiddle here, I mean that I allow for epsilon losses. So we do not get the precise estimate as in the Euclidean case, we allow for some epsilon loss here. So this corresponds to what Müller and Stein had, Müller and Zecker get more precise estimate without the epsilon loss, but I mean, this method, at least as it is written now, is more general, but for the time being, it doesn't, I mean, we need to tolerate this kind of epsilon losses. Okay, so as we mentioned, we can always reduce to time equal 1 and the convolution canons by the homogeneity and left invariance of the operator under consideration, and we can apply time propagation speed, so at least some part of this weak heuristic we mentioned before can be still applicable, at least to say that outside of a sufficiently large ball, it's a Schwarz tail, you can ignore the contribution, so actually you can just measure the L1 on all of the sufficiently large ranges. Okay? And then one thing that we do now is to somehow decompose this delta and the origin into somehow frequencies. And effectively what we're doing is to take the say space variable xu, we take the dual variable, frequency variable psi mu, and we do a dyadic decomposition for psi and for mu independently. So we have in principle dyadic frequencies in psi and then the corresponding dyadic frequencies in mu with possibly different parameters. And one question that immediately comes is how to relate what we already have in the estimates, that is this spectral localization, with the frequency localization we are trying to introduce. If you think of the Euclidean case that we just mentioned, if you put this spectral localization into the Fourier transform, it's automatically also a frequency localization, size about lambda. But here, in principle, they are different things. So how to relate them? And well, if you think a little bit, at least in terms of homogeneity considerations, the sub-Laplacian or the second order operator scales as a sort of second order under the automorphic dilation, so square root of lambda L actually scales like psi, whereas the mu variable, the second order layer variable, effectively scales like with the square of the parameter. So at least from a homogeneity consideration, you should think that psi will have something to do with lambda and mu something to do with lambda squared. And indeed, we can, by using appropriate vanishing moment information and cancellations, actually show that of all this kind of dyadic decomposition, most of the terms are actually again negligible for our purposes, and we can restrict to two regions, one where mu is indeed about lambda squared up to epsilon losses, and here it starts to see why we have epsilon losses, because they are somehow intrinsic to some of these decompositions, and similarly, so when A is about where mu about lambda squared, and the psi is at most lambda, maybe 1 plus epsilon, or the second region where instead lambda, so psi is about lambda and mu is much less than lambda squared. Okay, so here when I put the double twiddle again, I admit epsilon losses, and when I put this double twiddle here, I mean both inequalities with maybe different epsilon losses from one side and the other. And when I have this triple inequality, it's also a sort of epsilon loss, but in the other direction. So I want to say that actually here, to the case less than lambda to the square minus epsilon. Okay, so something like that, just to have shorthand for this kind of epsilon losses. And interestingly enough, this region A, actually we don't even need to develop the whole FIO sort of representation. So for this region, we can actually use a much simpler argument, which is somehow mimicking this Cauchy-Schwarz inequality kind of heuristic, but with an additional information which comes from this first layer functional estimate. Because by applying the first layer functional estimate, one can show that effectively there is no propagation in the x direction, at least for geodesics that start with this initial codirection in this region. I mean, it's a sort of technical part of the argument I won't be entering into, but somehow it's not too difficult by combining this weighted functional estimate on the first with weight on the first layer to show that for this region you have a much better behavior, just because you only see propagation in the u direction and not in the x direction. So you get something like lambda to the 1, because 1 is twice the dimension of the second layer divided by 2. You don't get any contribution for the first layer direction, but still that is enough because 1 is less than minus 1/2. I mean, because Heisenberg group, as I mentioned, is 3, so there is no problem. Okay, so it's quite easy to deal with that. And so the region which actually we need a new approach in terms of FIO techniques is this region B. And this one we split again, just for convenience in a sense, a small part where actually mu is very small, much smaller than psi. And this is what we call the elliptic region, because this one exactly corresponds to this kind of localization I mentioned before. If you are localizing in space, because here we are localized on X is in a small ball, then by taking this kind of angular sector sufficiently small enough, you can ensure that your principal symbol remains elliptic. And then you can just apply the classical FIO representation with the real phase, somehow what we did in this work with Detlef and Nicolo to get the necessary condition, at least for this small region, gives you also then combined with Segers-Stein argument the positive result. So this estimate will be -1 region. And so what really remains is the non-elliptic region, where now this mu is not allowed to go to 0, but it's bounded below by some multiple. Okay, so that's what remains to be treated. And there is where really we needed a different approach, this non-elliptic part that the FIO reach. So now we want to go towards this kind of FIO representation. So this kind of spectral localization is a bit funny if you compare it to the case of the elliptic situation where we wanted to have an initial frequency localization in a sort of isotropic fashion, so that the psi variable, the frequency variable, has a certain size. But here, in principle, you have two different frequency variables, two possibly very different sizes to the j and to the k. To sort of reduce the problem and sort of reduce to something a bit easier to understand, here we apply the automorphic scaling, which in the case of the Heisenberg group is a parabolic scaling that allows one to scale the frequency variable, the two components with two different parameters, one 2 to the n and the other is square. And if you choose this parameter appropriately, you can, after scaling, ensure that both psi and mu have the same size. So what happens is that now we have a new size, which is 2 to the n, which is somehow determined by the previous. So n is to j minus k after scaling. But the effect of this is, on the one side, to put these two scales of psi and mu the same. But if you scale frequencies, you also create scale space variables of the opposite scaling. And so this has the effect of actually bringing your initial ball, which was of fixed radius, to a ball of much larger radius, in principle, which corresponds to the scaling parameter. And not only that, you're scaling also the sub-Laplacian. So effectively, you get this kind of parameter in front of the sub-Laplacian, which effectively tells us that now we have to study estimates for large time. Okay, so instead of studying for small time the estimate on any kind of frequency localization, here we sort of fix a particular cone so that psi and mu are proportional to one another, but by scaling this needs requires us to actually study the similar estimate for large time. And that's somehow where we really needed to find a different approach to get this kind of FIO representations, which in principle makes sense only for small time in the neighborhood of the critical point. And then we were somehow lucky in a sense to discover that actually people studying this similar problem, actually propagational singularity problems, but for elliptic Laplacians, already had developed a method to get some FIO representation for the wave propagator associated with an elliptic Laplacian, which is global in time and space. And however, their representation involves no longer a real valued phase. In order to go beyond this kind of topological abstraction, they need to introduce a complex phase. And somehow what we did is to show that actually we can get an analogous representation also for the wave propagator on the Heisenberg group, and actually worked out an analogous representation that works on any two-step group. Here you see the phase function is very much expressed quite explicitly in terms of the geodesic flow. Here I'm using the similar notation as before for x t psi t as we saw course, we'll have two components, and I'm just taking the flow emanating from the origin because I'm taking the convolution kernel. So here, by translation invariance, I can just reduce to the flow emanating from the origin. So this real part is very simple and written in terms of the geodesic flow. And then you have this imaginary. And this is somehow a new kind of object that, however, it's important, it's fundamental for it to be there in order for this representation to make sense globally, to avoid any degeneracy in the Hessians and so on and so forth. And as it turns out, we have this kind of representation with an appropriate amplitude. We have a sort of density term which involves the mixed Hessian of the phase. And the amplitude, it turns out, is effectively the same as this spectral localization we had before, plus certain lower order terms. And here I'm omitting actually quite an important part of the argument. It requires a certain amount of work to show that this representation doesn't have problem in terms of a uniform estimate, for example, for large time. In the sense that Laplace, Sakharov, and Vasiliev were only interested in propagation of singularity issues, and so for them it was not so important to have uniform estimates in large time, or they were actually compact manifolds in their setup and so on. So really, they just show that some representation exists up to smoothing terms. But of course, if you're working in a non-compact manifold when parameters may become large, doesn't assure you that the estimates also remain uniform when you take parameters becoming large. And we could work out that actually on any two-step group, we have an appropriate form for the phase function that avoids any blow-up, also in the construction of this amplitude. So we do have a little bit of blow-up in time in this density term, but effectively it's under control. It's square root of the time. And in particular, of course, this is the simplest possible case. It's not exactly what we wanted, but this is also part of the issue here. When you put a bound on time and correspondingly on the space localization, everything is compactly supported. And then just by sort of homogeneity consideration, you can apply the modification of the Seger-Sorgenstein method, this kind of second-layer decomposition in angular sector and so on, and obtain the expected estimate. Here, you see that the frequency localization is about 2 to the n, so you get 2 to the n d minus 1 over 2, which in our case, I mean, 2 to the n is bounded by lambda, so we are happy. But the problem here is that actually we did all this work in order to treat the large time case. And okay, we may not have blow-ups in the amplitude expression, but there might be issues with the phase. And remember that one of the tools that are used in order to apply the Seger-Sorgenstein argument is integration by parts. And you have to integrate by parts a number of times inside to show that the various pieces in the decomposition satisfy the appropriate uniform estimate and one estimate. And the point is that if you start differentiating inside the phase function, which means you start differentiating inside these components of the geodesic flow, then you might have blow-up in time. Indeed, in the case of the Heisenberg group, and actually there are more general formula for the step groups, we do have an explicit expression for the geodesic flow. This kind of cosine and sine expression correspond to the spirals that we have seen before in the presentation of the geodesics, and the angular parameter you see is this 4. So T mu divided by 2 psi. In our assumption of localization, mu and psi are the same size, so effectively this theta goes like T. Okay? And so this is the localization, as I mentioned. So in particular, theta close like T. But the point is that if you then start differentiating the phasing, the frequency variable, well, you have all these terms, sine theta, cos theta, and so on. And so when you differentiate inside, this you have to differentiate theta inside of mu, so the frequency variables, and this pulls out factor C. And this is the problem that we have in applying just directly the Seger-Sorgenstein argument to this representation for large time, because this might lead to, if you integrate too many times by parts, you get many powers of T, and this is of course not what we would like to see. But on the other hand, that's the other somehow additional ingredient that we need here. So in order to avoid this problem, effectively we perform another decomposition and change of value. So the idea is that instead of considering the original theta, we split the values, possible values of theta, which is about 2 to the L, so the time parameter, the localization parameter, into some sort of discrete parameter quantity, so this k plus a small error, which now is just bounded. So it's arranging in an interval of length 1. So we split the interval where theta ranges into unit length intervals. So we have a number of pieces, but for each piece, now the remaining term only ranges in a limited set. If you try to implement this in terms of a change of variable inside mu, you get a new variable mu twiddle, which is related to mu to this one. So the full change of variable from the old frequency to the new frequency is not a linear change of variable, sort of scaling and shearing of the variable mu, which has this kind of 1/t inside. But at the end of the day, after this change of variable, the mu with theta twiddle does not longer have the t inside. So when you do the integration by parts argument with these new variables, you no longer pull out these dangerous factors. So the size of t has become this discrete parameter that for each of the pieces is just this constant in the sine and cosine. So when you differentiate, it doesn't really create any block because even the derivative of sine and cosine is the same shape. So they still remain bound. So the effect of all of this decomposition is that now our FIO is split into many pieces. Remember that you have this change of variables, so you have the Jacobian determinant also in the change of variable mu to mu twiddle that give you 1/t factor. On the other hand, you have this blow up square root of t in the density parameter, and so I just combine everything with this t to the -1/2 in front. And what remains after all these kind of changes of variables and related in the various objects are objects like this, where the new frequency localization, I just relabel mu twiddle as mu, is become not longer this kind of psi about the same size as mu, but mu in this case is just bounded like psi. But it's again a standard type of localization to another portion of this Segrè-Sogerstein annulus. And in this situation, one can show that these pieces are all the uniform estimate that one wants. So there are some additional consideration that one has to do in order to show that also the some space variables, despite them being large, they do not create problems. An important tool for that is actually exploiting this imaginary part term in the phase function that effectively produces some sort of Gaussian decay because I plus I -1. So this also helps actually in showing that there is no sort of problem with this space variables becoming too large, because effectively if they are, then the part of the contribution to the integral is actually negligible for our purposes. And so at the end of the day, by combining all this kind of information, we can apply to each of these pieces this Segrè-Sogerstein secondary decomposition approach to get an estimate, which again has this 2 to the n to the power of d-1/2. But now, of course, here we have more than one piece, so we have to put all the estimates together. And notice that we had this t-1/2 in front, but we have t pieces, so actually the contribution is like the time localization parameter to the n to the 1/2, and then each piece has this kind of contribution. So we do have a bit of blow up in time, but luckily enough, if you look back at what our spectral localization, so frequency localization was after this automorphic scale, actually 2 to the n times 2 to the n was bounded by that. And so even if we have this small blow up in time, it can still be absorbed into the other part and get the desired estimate. Okay, so this is in a nutshell the argument that somehow shows that with some modification and additional decomposition, actually the classical Segrè-Sogerstein argument can be applied also to get essentially sharp estimate for the wave propagator, spectral localized estimate for the wave propagator of the Heisenberg group. And interestingly enough, I mean, I showed you this argument for the standard Laplacian or the isotropic Laplacian of the Heisenberg group. But you can imagine that, for example, if you take a non-isotropic Laplacian, what would happen is that perhaps you have different components of this X in different parts of the first layer, for which you might have different parameters in front of the parameter theta. So maybe some maybe even non-commensurable parameters with irrational ratios.
So yes. What do you mean by non-isotropic?
Non-isotropic Heisenberg group, I mean that you take the standard Heisenberg group, you take the...
Dilation.
No. I just take the sum of squares of that form the sub-Laplacian, but I put coefficient in front of the vector fields.
Okay.
Different coefficients on any, and they may be irrational coefficients. So exactly, you no longer have the radiality, but this method can still be applied. And so this is beyond what Müller and Stein did for the wave equation, because they only considered the isotropic Laplacian in their work and used the radiality in quite an important way. The same is true for the Heisenberg type result of Müller and Zeger. Again, use the isotropic Laplacian on the H-type group, whereas this argument actually applies to METD groups without any reason of having radiality. And then what I was trying to explain here is that even if you put these coefficients, the effect would be to change a bit this formula by putting maybe some coefficient in front of this angular parameter. But the whole argument here doesn't really see this problem, because again, as soon as you do the appropriate scaling and shearing, then even if you have some constants in front of it, you have finitely many constants, and the derivatives of sine and cosine remain bound. With a bit more work, I mean, I am not writing out all the argument. You can do it on Heisenberg type or METD groups where there is a second layer variable which is also higher dimensional, so it's not so obvious what to do with this kind of decomposition, because here effectively we are using a lot the one-dimensionality of the new variable to do this kind of splitting into an interval and so on. Here, then you do have to do an additional decomposition into angular sectors in the TBA case, but it can be done. And it's nice to have this kind of argument that then one can play around with, and indeed we managed to obtain the same result also in the TBA case with an appropriate choice of the phase function to get again the desired estimates. Okay, so I think my time is up, so thank you very much.
Thank you very much, Alessio, for a great series of talks. Are there any more questions? Okay, if not, then let's start.
Okay, sorry. I will ask some of them.
Okay, so in that case, once again, many thanks, Alessio, for a great talk. We meet back in 11.
Alessio.
Relax.
Lo so.
Grazie.